Welcome all to this last session of PLMW. For this session, I will be the chair. I'm Robert Krabbers. I'm delighted to introduce the speaker for our second technical talk. It's Nadia Polikarpova from University of San Diego, where she is an assistant professor. So she will be talking about program synthesis, which is an exciting research area in programming languages. So the floor is yours.
Thanks, Robert. Okay. Hi, everyone. I hope you can hear me. Can you hear me? Yeah. Yes, great. All right. So, sorry? It is on. It is on. I can put it closer to my mouth. I don't know if that's any better. All right. So for this talk, I thought I would just go through like the very basics of program synthesis. So if you're already a program synthesis expert, unfortunately, you won't learn anything new from this talk. But that's the idea, right? So we want the new folks who have not heard about it ever before to get into it and be able to enjoy the parts of POPL that will be focusing on program synthesis. Okay. And so what I decided to do for this talk is just to tell you about a couple of things that I think of as big ideas in program synthesis that make a difference, that have a lot of impact. All right. So what is this program synthesis thing? Well, the goal that the overarching goal that we all have is to automate programming, right? So just like in other areas, automation helped us make things faster and with fewer errors. We want to do the same for software, right? And so the big picture is that we want to be able to describe what we want the computer to do using some kind of high-level specification, and we want to automatically convert that into a program, some executable code, right? And you might think, well, isn't that how the compiler also works, for example, right? So the difference here is that the difference in the level of abstraction between what we call the specification and the program is so large that usually you cannot just do a deterministic transformation from one to the other, but instead there's going to be some kind of search involved. So basically, the defining characteristic of program synthesis is that you will define some space of programs, some search space, and there will be some kind of search that will search for a program that satisfies the specification. Okay, so and when I say specification, what do I actually mean? Well, we've tried a whole bunch of different kinds of specification in the program synthesis community. So one of the popular ones is you're just giving examples of a program behavior. You can say, on this input, it should return this output, and so on, right? But that's not the only one. So for example, one possibility is you want to give a simple but slow program, and then you want to get a faster program as the output. You can describe what you want using some kind of formal logic. You can describe it using types. And lately, even, you can add natural language into the mix, right? So program synthesis area is very broad in terms of what counts as specification, right? So all of those things have been explored. All right? And so what is then the main challenge of program synthesis is that, well, because there's a search involved, right? And this program space is usually pretty large, right? So what I mean by program space, well, usually you say, I want to consider all programs in some kind of language. And usually it's some kind of small domain-specific language. But still, usually there are infinitely many programs that you can construct in this language. And so you want to explore this astronomically large space. And so the challenge is, well, the searching is really hard. How do we search in this giant space of programs, right? And most of the contributions in the field of program synthesis are about that, right? So how do we make this exploration of this huge space a little bit more efficient? All right, and so people have come up with a whole bunch of different algorithms for doing that, which you can kind of roughly classify into a couple of search strategies, as I would call them. So a very popular one is just enumerative or exhaustive search, where you have some kind of algorithm that just enumerates programs in some exhaustive order, one by one, and checks them against the specification. There are stochastic algorithms that are exploring programs in some kind of random order. There are constraint-based approaches. Those are the ones that using some constraint solver to actually do the search for you. And then as of recently, of course, you probably all know things like GitHub Copilot, right? So we're integrating some kind of learning-based, maybe neural network-based approaches into the whole mix. I will not really talk about that in this talk, but definitely also exists. All right, so this is sort of the big picture of what's out there, right? And so now to the main part of the talk. So let me present some things that I think are big ideas that make this sort of simple picture work. And a word of caution, this is by no means an exhaustive list, and obviously very, very subjective. So if you're doing work in program synthesis and I don't mention your idea, please don't be too mad. Okay. Okay, and so they, and also, of course, because the amount of time I have is limited, there are a ton more ideas that I'm very, very excited about, but I try to distill it down to like the very, very few important ones. The first one I'm going to talk about is what's called observational equivalence. The second one is called counterexample guided inductive synthesis, or CGIS. Obviously, we'll go into this a bit later. The third one is deductive synthesis, and the fourth one, sort of the general idea of learning while searching. Okay, so let's just start with the first one. Okay, what is this about? So for each one of these, I will tell you in which particular setup out of all of these combinations of like specification and search strategy this applies to, right? And this particular one, our first one, applies to the following setting. If your specification is given in terms of input-output examples, right, and your search strategy is this exhaustive or enumerative search, right? Okay, so example, right? So for example, maybe we want to synthesize a string transformation, right, that takes a string and returns a string that extracts a first name out of full name. And I could specify giving it this example, right? So my full name goes to my first name. Okay, so and what kind of program space do we want to consider? Well, let's now consider a very, very simple language of string manipulations that only has these 3 operations and 3 constants, right? So the operations are the following. The first one is string concatenation. You can put 2 strings together. The second one is slice or substring, right? So you can take a string and get a slice from an index to another index. Then you can obtain an index by finding an occurrence of a string in another string. And then you have 3 sort of constants or nullary kind of operations, right? X means input, right? So in our particular case, X would evaluate to Nadia Polikarpova. Then there's a constant for a space, right? Space character, and there's a 0, number 0. That's the only things you can use in your programs, right? You cannot use other numbers or other strings in particular. Okay, so given this language, can someone here tell me a program that would solve this example, or that would extract first names? Just like a general idea. Which operation should we use? Yeah. Mm-hmm. And then? And then you do substring, right? So that's what you can do. You can extract a substring from 0 to the position of space, right? So that's kind of what we're hoping our synthesizer would do for us, right? Okay, so how do we find this program, right? And one very popular strategy, even though it seems very simple and kind of brute forcing, but one very popular strategy for doing this is called bottom-up enumeration. Let me tell you a little bit about how this works. So just as a reminder, our specification and our search space are listed there on the right. So bottom-up enumeration, what it does, it constructs a so-called bank of programs, right, where we're going to store the programs we have already built. And then we're going to build new programs by combining. We're going to build larger programs by combining programs that are already in the bank, right? That's the whole idea. So in a little bit more detail, we will sort of structure our search by in the order of increasing size of programs, right? We will start by building all programs of size 1, and then 2 and 3, and so on, combining programs from smaller size, to get programs of bigger size. Okay, so programs of size 1, which programs do we have of size 1? How many? we have 3, which are our nullary operations or constants, whatever, right? So we can put these x in space and 0 at size 1. At size 2, there's actually nothing, so let's skip it for now. But just to see how programs of larger sizes are constructed, for size 3, right? So what are we going to do? We're going to go through all the operations that we have. So for example, we pick concatenation first, right? And so concatenation, the operator itself already takes up 1 unit of size. So we have 2 units of size left to distribute between the 2 children, right, of this concatenation. So we can use all combinations of string programs from the bank of size 1, right? Because we need size 2 in total. So for example, we would do concatenation of the 2 x's, then concatenation of x in space, and so on and so forth, right? We'll have 4 in total for this particular operation, right? So then once we're done with concatenation, we'll go to the next one. Next one is our slicing or substring. Well, for that one, we cannot find anything at size 3 because we need the sizes of children to add up to 2. There are 3 children, so that's not possible. So we'll just skip that. And for find, it's going to be the same, similar as what we did for concatenation, right? So you see, you get the idea, right? So you pick an operation, and then you combine the programs you already had at previous levels, right, to make new programs. So it's sort of a dynamic programming algorithm in that sense. OK, and then we do something size 4. Size 5, there's already too many programs to show you, so I don't show them all. And at size 6, eventually we will enumerate the program that we are looking for. Remember, that was the one, that was the solution for us. And it's a problem, right? So once we enumerate it, we test it on the examples, we see that it works. Great, right? So we will return the solution. OK, so this is how basic sort of bottom-up enumeration works. And it's nice, but as you can see, the size of this bank grows really quickly with the size of the programs, right? So if our solution is a bit larger, then it will get a very long time to get there, right? So basically, it explodes quickly. OK, but what is one idea for how we can sort of prune this bank, right? How we can remove some programs from this bank so that we don't have to enumerate so many programs? Well, the idea is some programs in this bank are actually redundant, right? And so what do I mean by that? So for example, if I look at this program, find xx, do you think it's the same, like equivalent to some program that we already have in this bank, to some different program we have in this bank? Which one? 0, right? Because this will always return index 0. So it is equivalent to that program 0. There's another one that's just like that, right? And so the idea is, well, we don't have to keep those redundant ones, right? So the redundant ones, we really should remove, OK? But there is more, right? So let's look at these 2 programs here. So in find, the string comes first and the substring comes second, right? So this first one, find space x, means find an occurrence of x in space, right? So that, OK, depends on how we define the semantics of find. But let's say we define it so it returns -1 because x does not occur in space, right? The second one will also return -1 because 2 spaces doesn't occur in x for this particular input, right? These 2 programs are not in general equivalent, right? For other inputs, they might return different things. But the big idea, and this is what is called observational equivalence, is that from the point of our synthesis problem, we don't care about any other inputs. We only care about what these programs evaluate to on the input that's given in the specification, right? Because think about it, because we only care about what it evaluates to on this input, we cannot if this program doesn't satisfy the spec on this input, the other inputs are not going to make a difference. And as you're composing programs together, other inputs are also not going to make a difference, right? So basically, the idea is the programs are also redundant if they're just equivalent on the specification. So in this case, we can also remove the second program. And so the idea is that so this is called observational equivalence, right? So when a program are equivalent on the inputs from the specification. And this idea is very powerful because, first of all, it's very easy to test, right? If you wanted to check if 2 programs are equivalent on all inputs in general, that's a hard problem, right? However, checking observational equivalence is very easy. You just evaluate it on these inputs, and you're done. And secondly, even more programs are equivalent than in terms of full equivalence. So you remove even more redundant programs from your bank, right? And so, for example, here I colored the different equivalence classes of observational equivalent programs, right, in corresponding colors. And as you can see, if we remove all the redundant ones, right, so if we only keep one per equivalent class, all of a sudden our bank becomes much, much smaller, right? You might think at this point, okay, does this matter? Because we still had to generate this program, then check if it's redundant, and then remove it. Didn't we do the same amount of work, right? But it matters a lot because remember, we are constructing programs of higher sizes from programs of lower sizes stored in the bank. So if we remove, for example, what did we have? At size 4, right, we used to have 2, and now we have just 1, right? So at some size, let's say 9, right, if we all of a sudden need 2 programs of size 4, sorry, 2 subterms of size 4, we used to have 4 choices, and now we have just 1 choice, right? So eliminating programs at lower sizes makes a big difference when you construct this savings compound, right? So when you construct programs of higher sizes. Okay, so here's the summary of the first big idea. Observational equivalence, the idea is that programs that behave the same on the spec are redundant, right? And we don't have to keep track of them. So we only need to keep track of one of them, and it makes a big difference because the savings compound at higher sizes. Okay, any questions about this? Yeah. Right. So because in this case, our specification was just one example, if you have more examples in your spec, you have to check if they're equivalent on all of them. And generally, the more examples you have in your spec, of course, the finer grained the equivalence classes will be, the smaller the effect of the observational equivalence will be. Yeah.
There are examples, right? You don't have the complete set. There are just examples of it. So how can you say, we don't have the complete picture of the input. We just have some examples. We can't remove programs that were equivalent only on that set.
Oh, but that's the only thing you're giving to your synthesizer. And the assumption is whatever program it returns that works on these examples is fine. That's the assumption about the setup. Whenever you're doing synthesis from examples, that's how it is. You're good with any program that satisfies the examples. Usually, you would want like the smallest one. That's why we were always keeping the smallest program that satisfies the examples. Yeah, there were other questions behind.
What if you happen to prune some program that is actually preferred, and you keep only the most concise, right? But in some cases, maybe you prefer other metrics.
Right, this is a great question. I mean, we were just assuming here that what you want is the smallest program. There's a variation of this same bottom-up numeration algorithm that orders programs by cost rather than by size. So if you have a cost function that's compositional, it will still work. Oh, there are a lot of questions. Let's take maybe one more and then take the other ones offline because I want to get to the other 3 cool ideas.
In what situation would you use this kind of example guided program synthesis? Because I imagine that in this case, maybe we could just use a lookup table for all the examples and say, here, we'll have the correct answer for all the given examples, and for everything else, we'll just pick some dummy value.
Do you mean you have a table for all possible programs that you can compose in this language?
Your examples would come in the form of input and what expected output is.
Yeah.
So then you could have a dictionary where the keys are the examples, the inputs.
Well, there's still a lot of programs that you could construct. So it would be hard to compile such a dictionary that would, contain all the programs that people could care about. Right. So of course, yeah. Okay. Maybe that was the part that was missing.
Can you paraphrase?
Yeah. So the question was, the reason. Okay. The comment was the reason you cannot just use a lookup table from inputs to outputs is because the reason you need the program is because you want to run it on other inputs later. that are unseen by the synthesis algorithm. Well, the example set is fixed from the point of the view of the synthesizer. That's the only thing that synthesizer gets to see. But then once it gives you a program, you can run this program on other inputs, right?
Let's say you pruned something based on the example set, but on other inputs, the two programs were different.
Well, right. So I mean, this is not a bulletproof solution. So it will give you what you asked for, right? What you asked for is a program that's correct in these examples. Of course, it has no guarantee that it will give you exactly the program you want, right? That it will behave correctly in other examples. Right?
Imagining what it's useful for. If you have like trouble imagining what it's useful for, think about Excel or like spreadsheet software, and what happens when you drag a cell with the like clever autocomplete. But this like generalized to programs. But you're still working with a very simple language when it comes to spreadsheet software.
Right. So flash fill, the feature of Excel. If you have never used it, try it. It's very cool. So this is using basically this kind of technology, right?
Small request to the audience, please don't start talking until you have the mic.
Okay, cool. I kind of wanted to show you a demo. Well, let's just go for it. Maybe, given that you've never seen flash fill, maybe I should have shown you flash fill instead. But I wanted to show you this tool that we developed called Snippy that is using this technology, right? So the cool thing about Snippy is that it's running inside VS Code, and it's showing you these things called projection boxes, which are basically showing you the values of all the relevant variables at every line in your program, right? So for example, here, inside this function task, I have an input variable name, and I have some temporary variable res, and it's showing me what the values of these variables are everywhere, right? And so it will live update if I change it to something. And this tool has a bottom-up enumerative synthesizer integrated inside of it, right? So for example, if I want to extract the first name from this name input, right? So here I used a more interesting person than myself. Also more interesting because does any of you know who Augusta Ada King is? What is a different name that she's known by? Yeah, Ada Lovelace. It's the same person. So if I want to extract the first name, what I can do is I can type in double question mark. Ugh. The tool is misbehaving. OK. And then I go inside this projection box, and I basically type in the value that I wanted to have, right? So for example, here I want Augusta, right? And it will just tell me, OK, you can do this, right? Which is basically the same program that we've seen on the slide, but in Python. I can also do more interesting things. So for example, what if I wanted, sorry, it has some UI issues. This happens when you're running it live. Let me try. I'll try to reboot, but we'll see if this works. OK, maybe I shouldn't waste time on this. But basically, it's a tool that uses this technique, right? And it's pretty cool. So OK, let me try. OK. So now if I just do a.k, right? So for example, not just extract the first name, but I want to extract initials, separate them by dots. OK, so it can do like a little bit more impressive things like this one, right? For example. So this thing really works. So this technique was proposed at the same time, basically, in 2 different papers in 2013. So if you want to go to the origins, I recommend to read these papers. If you want like a nice description of bottom-up enumeration and this observational equivalence thing, actually, Schroeder's paper, Schroeder is sitting right there. I think it has a really, really good description of this kind of stuff. So I can really recommend reading this one. All right, so this was the first one. Let's move on to the second one. The second one is, the second big idea I want to show is counterexample guided inductive synthesis. So here, the setup is we are now not trying to generate a program from examples, but rather we either have like a simpler program to start with or some kind of logic. And the problem that we have is we have some kind of way to search from examples, but we need to adapt that kind of synthesizer to work with this other kind of specifications, right? Okay, and an example problem that I'm going to be using here is, so this is a transformation on bit vectors, right? And the problem is to isolate the least significant 0 bit in a bit vector. So for example, if you have this so what does it mean to isolate? It means that you find the least significant 0 bit, and then you put 1 in that position and 0 everywhere else, right? So that's what you want to do. And of course, this kind of transformation is easy to implement as a loop, iterating through all the bits, right? And as you see the first 0, right, so you sort of put 1 in there and you return. But this program is not entirely satisfactory because, you know, it iterates over all the bits, and we would like to do it more efficiently just using bitwise operators, right? So basically, the setup here is, as a specification, we are using this loop, right? And then we are saying, well, but the program space is such that you're not allowed to use the loop, right? The only things that you're allowed to use are, well, the input and the bit and constant bit vectors, but also things like bitwise negation, bitwise plus, plus, bitwise OR, and XOR, right? So you're only allowed to use the simple kind of expressions. And then the question is, well, can we even do it? Like, what is the program that can do it? And so to show you that such a program exists, I'm actually going to give you another demo of a different tool, a tool called Sketch. So here, you don't have to read this, but this is basically how you tell Sketch your specification, right? So this is, I wrote this loop program, and this is how I specify my search space. But then we can run Sketch from here, and we'll think for a little bit. Unfortunately, the output is not super readable either, but basically, what Sketch is telling us is, so this long string of 1 with a bunch of zeros is just saying, let's take the number 1, right, a 32-bit vector, which is the number 1. And then what we're going to do with it is we're going to do x plus 1, like x is our input, and not x, right? So it's Sketch is claiming that this program solves a problem, right? And if you think about it for a little bit, so this is the same program written more concisely. If you think about it for a little bit, you'll see that indeed this is a correct solution, because if you take your input and you add 1 to it, what is going to happen is a string of, like, the rightmost bunch of 1s will turn into zeros, and the next 0 will turn into 1, right? So it almost achieves what we want, except all the 1s to the left are still there, and we kind of need to get rid of them, right? And so then what negation does, it inverts every bit, right? And now if we, now you can observe that, sort of the stuff to the right of the left of the least significant 0 now matches between the negation and plus 1, right? Whereas everything else is opposite, right? So now if you AND them, it will 0 all these 1s that are to the left, right? Okay. So basically, Sketch can synthesize this program from this specification, right? But the question is, how does it do that, right? So, I mean, of course, the naive way of doing this would be, to, again, enumerate a bunch of programs. But then, like, as you're enumerating those programs, how do you test if they're correct? Well, do you need to test them on all inputs that they're equivalent to the reference implementation? That would be, like, super, super slow, right? But there's a better way of doing that, right? And this is where this idea of counterexample guided inductive synthesis comes from. But to illustrate this technique to you, I will first tell you about a game, right? And then the reason I'm telling you about this game is that this game works exactly like this technique works. And so if you understand the game, you will understand the technique also. So the game is played like this. Let's say, so the game is played with these plastic pieces, right? And so let's say I'm the teacher, and I made up a secret rule for how you can arrange those pieces into a structure. The structures are called cones for some reason, right? And so I'm now showing you 2 of these cones, and I'm saying that the left one satisfies my rule that I just made up, and the right one does not. And now you need to guess which rule I have in mind. So take a guess. What do you think I had in mind? Yeah. Yeah, they're stacked. Well, unfortunately, you guessed the rule from the first try. So the rule I have in mind is that all the pieces should be grounded. But the idea that I wanted to illustrate is that, for example, you would say something else, right? You would say, for example, there should not be any red ones, right? And then I would say, no, that's not the right rule. And then I would build a new one where, for example, it has a red one, but they're all grounded. And then I would say, well, this one actually satisfies my rule, but does not satisfy your guess, right? And then you will take more turns, and then eventually you will guess the rule. OK. Yeah, it's fine. So is everyone on board with how the game works? OK, exactly the same idea with sieges. So basically, the game works like this, right? You take the initial the learner sees the initial cones. And then what might happen is that the learner says, well, I really don't know. There's no rule that I can think of, right? Then the learning fails. Or it can take a guess. Then the teacher would say, well, great, this is what happened now, right? The learning succeeded immediately. Or if the learning doesn't succeed, the teacher gives you a new cone that differentiates your guess from the real rule. Sieges works just like that. It's basically the Zendo of program synthesis, right? Except that instead of a learner, you have an inductive synthesizer. What do I mean when I say inductive synthesizer? It means something I can synthesize from examples, right? From input-output examples. And instead of a teacher, I have something called verification oracle. What's a verification oracle? It's something that can take a program and take a spec and say either this program is good on all inputs, or it can give you an input on which the program is bad, is incorrect, right? And that input is called a counterexample. And that's where counterexample guided inductive synthesis comes from, right? Right. And so on our example of isolate 0, right, so maybe we will start with the initial example that would just say 0 maps to 1, right? And then the inductive synthesizer might say, oh, I know, it's just the constant 1. That's the program. And then the verification oracle will be like, no. Because that doesn't work, because if your input is 1, the output should be 2, right? So constant 1 doesn't work. OK, then the inductive synthesizer looks at both of those examples and says, oh, maybe it's plus 1, right? Because 0 goes to 1, 1 goes to 2. Maybe it's x plus 1. Verification oracle will be like, no, it's actually, if the input is, what is this, 5, the output should be 2, right? So please consider that example as well, right? And then the inductive synthesizer is like, OK, I guess it's this program. And then the verification oracle is like, great. OK? Yeah.
Is the verification oracle still saying that it's correct on all inputs with respect to some specific corpus, or is it more broader than that? Is it still somehow coming up with a wider set of what the valid inputs could be?
This is a great idea. So the general idea of sieges is sort of parametric with respect to that. But so the way it's done in Sketch, the tool that I just shown you, right? So it actually uses a constraint solver to do both of these things, both as an inductive synthesizer and as a verification oracle, right? And this constraint solver can consider the space of all bit vectors, right? So in this case, the space is still bounded, right? But there are a lot of inputs, and checking them one by one would be very expensive. But the constraint solver is smart enough that it can actually check all of the bit vectors of a certain bit width, right, in a short time, right? So what you saw in Sketch is guaranteed to be correct for all bit vector inputs of a certain size.
Do you also know about work on making the oracle smarter, like choosing pedagogically better examples? Does that happen automatically, or is there like a human in the loop there? What are your thoughts on that?
This is a great question. So in the tool that I showed you, there's basically no guidance there, right? So just whatever the constraint solver picks. There's a whole line of work on It's usually called question selection, where people try to come up with better ways of coming up with counterexamples. So usually those techniques end up like not really saving you much time in this fully automated setting, because it takes so long to pick a good example that you could do like 10 iterations in that same time, right? But there's recently work that I believe will appear at UBSLA. They have some interesting like approximate techniques for doing this. Yeah.
So you said that, for example, in this case, the verification oracle can say that your program is correct on all inputs of certain bit width, but I imagine that the general case would be a little more difficult. Like, how can you say program equivalence for like if the input space is infinite, for example?
Right, exactly. So verification in general is an undecidable problem, right? So kind of the name of the game in a lot of synthesis techniques is we restrict our domain of the programs that we're reasoning about, right? And of the input sometimes, right? To make these verification and also inductive synthesis problems decidable, right? So here the trick is bounded domain. We're dealing with bit vectors, right? Sometimes the trick is, oh, let's limit the space of programs to things that SMT solvers can reason about in a decidable way. And then you don't have to limit the input space, but you have to limit the program space. And then actually, the next technique I was going to tell you about also deals with a more general problem of unbounded inputs and actually complicated programs, if we get to that.
Yeah, so maybe that's a good reason that we should move on.
Right. So we're more than happy to answer your questions offline.
Yeah, so
but
don't
there are a lot of
hesitate to talk to Nadia afterwards.
Okay, so the big idea here was to iteratively learn from counterexamples. So basically by pairing an inductive synthesizer and a verification oracle. And the cool thing is that we can use, depending on the program space and the input space, but often we can use a constraint solver to implement both the inductive synthesizer and the verification oracle. And so a good paper to read about that particular sketch tool is this program sketching paper. It's not the first paper on this, but it's a journal paper, so it's more accessible, I think, better written. Okay, idea number 3. How much time do I have left? Like less than 10 minutes, right?
You have 7 minutes.
Cool. So, well, I can skip number 4. It's too fancy. So idea number 3 is deductive synthesis. So this happens in the setting where your spec is some fancy logic or maybe some fancy type system. And in particular, we are worried about this problem of unbounded inputs. And it's kind of really hard to even tell if a particular program that we're looking at satisfies the specification, right? And also, we might be interested, well, we actually kind of care that the output that we get is correct, right? Because remember, in the first setting, and this is what you all alluded to, when we're synthesizing from input-output examples, you're only guaranteed that the program is correct on those examples that you gave it, right? But here, we actually want to prove that the output is correct. And so basically, just to step back, we kind of have 2 challenges that are in this space, right? So first challenge is that we have this huge set of programs that we want to explore, huge space of programs. But the second challenge is, even if we pick a particular candidate program that we want to check, this is already a very hard problem under this setting, right? And so you might be thinking, well, Nadia must have gone crazy because she's saying you take 2 difficult problems, you put them together, and somehow it's going to work, right? But that's exactly what I'm telling you, right? So it turns out that this idea of deductive synthesis is basically what it's telling you, that sometimes, even though looking for a program is hard, and looking for a proof for a particular program is hard, but if you are looking for a proof from the beginning, right, and using that to find a program, that can be easier. So basically, the idea is look for the proof to find the program. Another way to think about it is let the specification guide your search, right? And so let me give you an example so that you know what I'm talking about. So let's say now we want to synthesize the C program, right? And when I say C program, it's like well, think a simple language, but it's C-like in the sense that it has pointers and you can write anywhere in memory, do all this crazy stuff, right? And this is like the very, very simple example, but basically you want to synthesize a program that swaps the values of 2 pointers, right, x and y. And so how would you describe to the synthesizer what you want this program to do? Well, what you want to describe is something like, well, in the start state, before I execute my program, my memory or my heap looks like this, right? I have these 2 memory locations pointed to by the pointers x and y, and they have some values a and b. I don't care where they are, right? And then I want to say what my heap looks like after executing this program. And I say, well, after executing this program, I still have these 2 memory locations. They're still pointed to by x and y, but the values are swapped, right? And so, well, it's not very easy to give synthesizer some pictures, right? Some pictures of memory as input. But thankfully, there are program logics that allow you to describe these pictures sort of using formulas, right? But they look very similar to these pictures, basically. And one of them is separation logic. It's a special logic for talking about programs that manipulate the heap. And you don't really have to know anything about it. You just have to look at these formulas that I'm showing you and basically see how they correspond to the pictures, right? So this first formula is basically telling you, well, there's a pointer x that points to A, and there's a pointer y that points to B. And because there's a star in between them, it means that they're 2 different pointers. They're not in the same place. OK, and then we can say, in the start state, the first formula holds. In the end state, the second formula holds. So here you might have noticed that x and y are kind of upright and a and b are kind of cursive. That's because x and y are program variables that our synthesizer can use in the program. That's because they are the inputs to my arguments to my function, whereas a and b are just like some ghost values that you cannot use in the program, right? Because they are not parameters to the function. And so, so we are in the setting where we have the spec, and we are searching the space of C programs. And what we want to find is like a very straightforward implementation of swap, which just reads out the values from x and y and then writes them back to both x and y. OK, and it seems like, OK, this is a super simple program. How can it be possibly hard to search for it? But if you think about it, the problem is that C allows you to do whatever you want with the memory, right? So if I start searching for this program without looking at the spec, right, I might think, what should be the first instruction of my program? OK, something that makes sense is to read the value from pointer x. But I might also read from x with an offset 100, because, like, why not? You can do that in C. Or I can, write x into y, or I can malloc some amount of memory and then go do stuff there, right? No one is telling me not to do that, right? The point is, C doesn't stop you from doing, like, neither its type system, nor its syntax, nor nothing stops you from doing that stuff, right? But separation logic actually stops you from doing some of those things, right? And if you look at the spec as you're searching, then you will not do those things. Like, well, you will do the first one, but not the other one, right? So just to illustrate this using pictures, let's start from the spec that we had, right? We basically say we need to go from this state at the top to the state at the bottom, right? Well, let's look at what we have in that top state. Well, we have some pointer x pointing to a value a. Well, why don't we read it out, right? Maybe we will need this value later, right? Similarly, we have the same thing with y. OK, now let's look at our post state. Well, in our post state, we say, well, x now points to the value of some program variable b1. In the post state, it should be pointing to that. But in the pre-state, it does not yet point into that. So we should just write it, right? So we should just write b1 into x. Why not? And the same thing with y. And then finally, we got to the state where our pre-state and our post-state are the same. So there's nothing more to do, right? And we are done with the synthesis. So you can see, if you look at the spec as you're doing the synthesis, it was guiding you, and you didn't have to try any silly things. OK? Makes sense? OK, so the big idea is look for the proof to find the program, because the space of proofs is often more restricted than the space of all programs. And as a bonus, you get a provably correct result. Can I show one demo and then
Very, very brief.
Okay, be done with it. Okay. This is just a demo to show you that it cannot only do swap, but it can do something more interesting, right? So you don't have to get into the details of this example, but basically, let's say you have a binary tree in memory, and you want to flatten it into a double linked list. And you notice that you can actually do it in place without reallocating memory, because the nodes of a binary tree and the nodes of a double linked list are the same size, right? So you can just do some pointer manipulation, and it will work out. And this is a little bit tricky to do, to figure it out by yourself. It's not a trivial program, but you can use a synthesizer to give you this program by basically giving it a specification that says, well, in the pre-state, I have a tree at this pointer, and then in the post-state, I want to have a double linked list at this pointer, right? The same pointer. This is how it's going to be in place. And I just wanted to show you how our synthesizer does that. So one of our synthesizers called Suslik can do this. So this is the spec. Basically says we have a tree in the precondition. We have a list in the postcondition. So let me click it. And so you see it's doing the search, and it's basically showing you how many different nodes, proof nodes it export. And after maybe 5,000 something, it should find the solution. Wait for it. Okay, 6,000. So it basically finds this program that is kind of it actually conjectures a recursive auxiliary, right? So it says basically flatten the left subtree, flatten the right subtree. And what this auxiliary does is concatenates the two resulting lists, right? So it's a non-trivial program that it was able to synthesize from the spec. Okay, that's all I have time for. Here are some references for papers from this space. Didn't have time to talk about this, but I can tell you about it in the break. But thank you for your attention.